So welcome to the Mechanics Lectures for Physics 1A. I'm Associate Professor Elizabeth Angsman, or otherwise just known as Liz. My office is in the old main building in room G61F, and my office hours, which is the hour that I'll make sure that I'm in my office in case you have questions to ask, is Monday from 2 to 3 p.m. My email address is given here, and you can also find it all over Moodle. So we're going to start with some administration matters. I'll show you the Moodle courses. Everything that you need to know about this course is on Moodle. Okay, so when you log into Physics 1A, it should look something like this. Up the top, you're going to have the next 3 weeks, and this will be a helpful summary for you about what's due each week. Each week I'll also post up an announcement which will be emailed out to you as long as everything's set up in your forums properly about what's coming up in the following week. So in order to see everything, we'll just need to open all the toggles. So you've got your course information, you've got your syllabus, course outline, course pack. So from your course pack, you can download and print the laboratory manual and homework booklet if you want to. Alternatively, you can buy the lab manual from the bookshop. You've also got past exams, which will be useful for studying once you get a bit further on in the course. Now you've got your lecture notes. You're able to download the lecture notes from under the mechanics heading. If you miss lectures, you may want to use these web stream lectures in order to catch up. Below that, you've got your laboratory section. So before each lab, there's a pre-work test that you'll need to do to help you prepare for the lab. There's also a safety induction that you should complete in the first week. So below that, we've got the problem solving workshop. So these are the things known as other in your timetable. So in week 1, you'll be learning about uncertainties in the problem solving workshop. You can access the resources that will be used in class here. Now, each week, you're going to have a quiz due. So each of these quizzes has 4 questions, which are based on the 4 lectures from the previous week. So the first of these will be available at the end of week 1, and it'll cover the content which you've learned in week 1. In order to get ready for it, it's a good idea to do this stack orientation exercise. This will teach you how to input answers into these quizzes. Twice during the term, you're then going to have quizzes which are pulled from the same bank of questions available to you, and these will be held in the first year lab, but you'll find out more about those later. With the at-home quizzes, you can do them as many times as you want, and your highest mark counts. Now you've also got access to homework sets. You have videoed solutions to each of these. These will be put up progressively throughout the term. It's a good idea to practice answering the questions yourself before watching the solutions, which is why they're not all just available at the start, but they will all become available during the term. And then we've got discussion forums. So if you have any questions about the course, you can ask them here. Administration forum, so that's just questions about anything. Mechanics, so that's if you've got questions about mechanics. Quizzes, that's if you've got questions about these quizzes here. And lab, obviously if you've got a question about lab or problem solving workshops. Okay, so that's the Moodle site, but let's get back on with the mechanics now. Okay, so some of this will be familiar to you if you have studied HSC physics, or if you have already completed the Maths 1A course. Some of you will be studying Maths 1A at the same time. So we have 2 different types of quantities. We've got vectors and we've got scalars. Vectors are things that have a magnitude and a direction. Scalars are things which just have a magnitude. So we can identify each of the following quantities as either a vector or a scalar. Now, temperature is a scalar. We can't have a direction to a temperature. Temperatures can be increasing or decreasing, but the temperature itself, like 22 degrees C, doesn't have a direction, so it's a scalar. Mass is the same. We don't have 1 kilogram north or 1 kilogram with any direction. We just have the mass 1 kilogram. Velocity is a vector. So when we're talking about the velocity of something, we need to give a direction with it. So we could give a velocity of 5 meters per second north, for example. Time is another scalar. This one doesn't have a direction, just a magnitude. Distance is actually a scalar as well. So when we give the distance between 2 points, we give it as 5 meters. We don't give it as 5 meters north. If we were giving it as 5 meters north, it would instead be a displacement. So distance and displacement are very similar to each other, as we'll see very soon. But displacement is a vector having a direction, while distance is just a scalar, so it's only got the magnitude. Now, you'll learn to write vectors in unit vector notation in Maths 1A. So some of you have probably already seen this, but for others, it's new. So unit vectors are vectors which have magnitude 1. That's why they're called unit. So a unit vector in the x direction is written with the letter I, and we put this little symbol over the top. The symbol is called a hat. So this represents a vector with a magnitude of 1 in the I, which is the x direction. Now j is a unit vector in the y direction, and k is a unit vector in the z direction. So if we want to write a vector in unit vector notation, such as this one, let's have a look at how we can go about it. So with this vector, along the x-axis, we've got this length here. So if we drop this line down here, now hopefully from trigonometry, you remember that if we want to work out this length here, we'd work it out as 10, which is this length here, times cos 30. So 10 cos 30 is equal to 10 times root 3 on 2, which we can write as equal to 5 root 3, or we can evaluate it and write it as 8.7 meters. So that gives us the length of this side here. And so we've got 8.7 I. So because I'm writing this by hand and I can't write bold, I've put a little squiggle underneath my I to show that it's a vector. And then the y direction, the j direction, is up here. So this is going to be given by 10 sine 30. Sine of 30 is a half, so this will be 10 on 2, which will be 5. So we'll have plus 5j. So that's how we write this vector here in unit vector notation. Now, a hint, usually it's much easier to solve problems in unit vector notation than to try using the vectors in this format here with a magnitude and an angle. Okay, now we've briefly discussed bits of this before. So we discussed that scalars have a magnitude but no direction. So examples of scalars are distance and speed. So speed is equal to the distance over the time, but again, we'll be looking at that in more detail very soon. Vectors, the equivalent vectors are, for distance, we've got displacement. For speed, we've got a velocity, which is a displacement divided by the time. And then for acceleration, we've got change in velocity divided by change in time. So we'll be looking at acceleration more next lecture. So now if we want to show something is a vector, we can write it in boldface, which works if we're typing, or we can draw a squiggly line underneath it, which is usually what I do when I'm writing on the board. Or we can put an arrow on top of it. So all of these are ways of showing that the quantity that we're talking about is a vector, so it has a magnitude and a direction. So let's consider distance and displacement, which are similar but slightly different. So distance gives the total path length along which an object has traveled. So for example, if I was to consider a particle which went loop-de-loop and back to its starting point here, then the distance it's traveled is the length of this line here. Displacement, on the other hand, is given by the change in position. Now, there's quite a lot going on in this equation. In physics, we often use delta, which this is the Greek letter delta, the capital delta, to represent a change in something. So this is saying the change in x or the change in position. So the displacement is given by the change in position, which is xf, where this f stands for final, minus xi, where this I stands for initial. So you'll come across the change in something as equal to the final something minus the initial something an awful lot as we go on in physics. So if we were to calculate this displacement here, well, the final position is here and the initial position is here. So these two are the same, and so the displacement in this case is 0. So let's do a couple of examples. A particle travels around a circle. Okay, so let's draw a little diagram. It's always useful in physics to draw a diagram. So it's traveling around a circle. The circle has a radius r. If it travels once around the circle, okay, so it can start here, it goes once around and comes back. What distance has it traveled? Well, the distance it's traveled is the circumference of the circle. So that's given by 2 pi r, the circumference. And what is its displacement? Well, we know that the displacement is equal to the final position minus the initial position, and these are the same. So this is equal to 0. So the displacement is 0. Example 2. So a boy walks 10 meters north. So let's have our boy starting here. So this is x initial. He then walks 10 meters north. So here he is. This distance here is 10 meters. And then he walks 5 meters south. So now he's walking down here 5 meters. And this is where he ends up. So this is x final, the final position. And we're asked, what is his displacement? Well, his displacement is equal to the final position minus the initial position. So if we call this place the origin, then the final position, looking at this, if it's 10 up and then 5 down, this distance here must be 5 meters. So this is equal to 5 meters minus the initial position, which is 0 meters. So this is equal to 5 meters. So his displacement is 5 meters. The distance he's traveled, well, he walked the 10 meters up and then he walked the 5 meters back. So this is 10 meters plus 5 meters, and so this is equal to 15 meters. Now, because displacement is a vector, I should have given a direction with my 5 meters. So I should have said this was 5 meters north. Back on the last example where it was 0, if something 0, 0 doesn't have a direction, so we didn't need to worry about it in that example. Okay, so what you might have seen us doing there was adding two vectors. So we're going to have a look now at a couple of different methods that we can use to add and subtract vectors. So method 1 is the head to tail method. So with that, we need to know how to represent vectors to start with. So it's useful to represent vectors as an arrow. The arrow head shows the direction that the vector is heading. And then we call the arrow head the head, and the other end of the vector is called the tail. So which is why we're adding them head to tail. So let's see how we can do that. Let's say that we want to add this first vector here, which is 10, and that's 45 degrees above the horizontal, to 10 this way. In order to do that, we add them head to tail. So here's the head of the first vector, and here's the tail of the second vector. We join the tail of the second vector to the head of the first vector like that. So that has been done for us here. And now what we need to do is evaluate this resultant vector here. So you probably remember from school how we can do that. We can use trigonometry. In this case, we can work out what this angle in here is. That angle in there is 90 degrees. If this angle here is 45 degrees, then this angle here must be 45 degrees as well. Alternate angles on parallel lines. So that tells us that this angle in here is 45 degrees. So the total angle around here, we've got the 45 plus the 90. So this is 135 degrees. And so using our cosine rule, we've got a squared is equal to b squared plus c squared minus 2bc cos a. And so this is our angle A, and this is side A. And we've got sides B and C. And so we can say, well, this is 10 squared plus 10 squared minus 2 times 10 times 10 times cos 135, which gives us our A squared is equal to 341, which gives us our A is equal to 18.5 meters. Now, this is a vector, so we also need to give a direction. So it'd be nice to find out, well, what's this angle here? Let's call this angle here theta and try and work out what it is. Well, what we can do is we can work out what this angle in here is. Let's call that one phi, and we can use our sine rule. So we can say, well, sine phi over the opposite, which is 10, is equal to this one. This is our angle A, which is 135, over A, which we've now worked out. And so this gives us, rearranging, we've got phi, because we take the inverse sine of 10 times sine 135 divided by 18.5, and we end up with phi is equal to 22.5 degrees. So if that's 22.5 and this whole thing here is 45, that tells us that this thing is 45 minus 22.5, which is also 22.5. So we've got A is equal to 18.5 meters, and this is 22.5 degrees above the horizontal. Sorry, the pencil's not picking up especially well right now. Okay, so that's one way that we can add these two vectors together, by adding them head to tail. And you'll notice I represented the resultant, which was going from the tail of the first vector to the head of the second vector, with a double arrowhead like this, which is a notation that we commonly use to show that something is the resultant vector. Now, if we want to subtract vectors, so if instead of adding these two vectors, we wanted to subtract them, what we need to do is add them, but flip the vector which is being subtracted. So this is equivalent to that plus this vector here. So then what we do is we take the head of the first vector and we add the tail of the second vector to it. So we're going to have something like this, which is what's drawn down here. So then once again, we can go back to that long method using lots of trigonometry to work out what this is. So if we call this side A and this angle A in here, we can work out what angle A is, because this line is parallel to this line. This is a horizontal line, another horizontal line. So if that's 45 degrees, then alternate angles on parallel lines, this is 45 degrees. And so we have A squared is equal to B squared plus C squared minus 2BC cos A. Substituting in 10 squared plus 10 squared minus 2 times 10 times 10 times cos 45. And solving this, we end up with A squared is equal to 58.58. And so this gives us A is equal to 7.65. But then once again, it's a vector. So we need to work out the angle. So what we'd like, one way to do it is to find out what's this angle in here. So that part there is 45 degrees because these two sum together to give 90. So what we can do is say, well, sine of theta plus 45 over 10 is equal to, we know A now, so this is sine of 45 over 7.65. And so solving this, we end up with theta plus 45 degrees is equal to 67.5 degrees. Sorry, I'm not sure why it's not writing very neatly. And so theta is equal to 22.5 degrees. And so this is 7.65, 22.5 degrees left of vertical. Okay, so doing it that way took a bit of time, but there is a faster way to do it. We can also add and subtract vectors by breaking them into their individual components. So let's do that now. Now we've got, this is the same original vector here at 45 degrees, but we've now split it into a horizontal component, which we can calculate as 10 cos 45, and a vertical component, which we can calculate as 10 sine 45. So just using our rules from trig, we know that this is equal to 10 on root 2, and this is also equal to 10 on root 2. So this one here is in the vertical direction, so this is J, and this one here is in the horizontal direction, so I, and this vector, this is in the horizontal direction, so this is I. So when we're adding vectors component-wise, we add all the vectors in the same direction. So we've got I times 10 on root 2, plus we've got 10, and then we've got this one here. So this is 10 on root 2, J. So that is one way that we can write this total vector. We can also use a calculator to evaluate it, and if we do that, we can write it as 17.1i plus 7.1j. Now it asks us, does it agree with the result you obtained adding them head to tail? Okay, so if we want to work out what this will be when we add these head to tail, then we've got 17.1 this way and 7.1 this way. So adding these like this, we just use Pythagoras' theorem because these are at right angles with each other, so we don't have to worry about that cosine rule. So this is the square root of 17.1 squared plus 7.1 squared, and evaluating that, we end up with 18.5, which is the same as what we got as the magnitude of the vector when we added them that first way, head to tail. Now we should also check the angle, so let's calculate this theta. Now we know the opposite and we know the adjacent, so we can use tan theta. So tan theta is equal to 7.1 over 17.1, and solving this gives us theta is equal to 22.5 degrees. So we've got 18.5 and an angle of 22.5 degrees above the horizontal, which is exactly the same as we got last time. So we're asked here which method is easier. Well, at least for me, I found this method, breaking them into components and then summing them, took a lot less time. So if given the choice, I would use that method. Now, if you want some practice in homework set 1, for Phys 1121, there's questions 3 and 4, and for 1131, there's questions 4 and 5. Okay, so we've seen how to add vectors now, and we've seen what displacement and distance are. So now what we're going to look at is how to calculate the average velocity and speed. So the average velocity is given by the equation, which is change in x, which is our displacement, divided by the change in time. So this is the final position minus the initial position divided by the final time minus the initial time. Now we can also calculate an average speed. The average speed is given by the total distance traveled. So distance, that was the total path length over which our object went, divided by the change in time. So question, do average velocity and speed have to have the same magnitude? So the answer to this is no. If we think about that particle which was going around a circle, then the total displacement, once it had gone around the circle once, was 0. And so the average velocity would be 0. But the average speed was the circumference of the circle divided by however long it took to go around the circle, which wasn't 0. So they don't have to have the same magnitude. Now, we can also calculate the instantaneous velocity and speed. So this tells us how fast something is traveling at that instant. So to do this, the instantaneous velocity is given by the limit as our time interval becomes really, really small. And it's the change in the displacement over that time interval divided by the time. So this is dx dt. And the speed is just the magnitude of this instantaneous velocity. So this is the instantaneous speed. So in this case, obviously they do have the same magnitude. It's just that the instantaneous velocity also has a direction as it is a vector. Okay, so let's have a look at an example. So in this example, we've got a particle moves along the x-axis. Its position is described by the equation x is equal to 5 plus 2t minus t squared. And we're going to work out the displacement of the particle in the first 5 seconds, the distance that it travels in the first 5 seconds, the average velocity, and then the instantaneous velocity of the particle at a couple of times. So let's just pull up a separate page to do the working for this on. Okay, so in this question we had x is equal to 5 plus 2t minus t squared. And in the first part, we're asked what is the displacement of the particle in the first 5 seconds. So we know that the displacement is equal to the final position minus the initial position. And so the final position, that's x when t is equal to 5. So that'll be 5 plus 2 times 5 minus 5 squared. And then we need to subtract off the position at the initial time, which is t equals 0. So this will be 5 plus 2 times 0 minus 0 squared. So this will be 5 plus 2 times 5, so that's 5 plus 10, 15 minus 5 squared, which is 25. So this will be 15 minus 25, and then this term's 0, this term's 0, so we've got minus 5, and so this is equal to minus 15 meters. And this is along the x-axis. That's what this x shows. And then part 2 is actually a bit harder because this asks us for the distance. So what we need to work out is exactly how is this particle moving. So really what we'd like to do is plot a little diagram showing if this is time here, what's x. So at time 0, we calculated it here for this part, its initial position, it was at 5 meters. But what it's tracing out here is a parabolic path. So there's a few different ways that we can sketch this parabola. One way to do it is to realize that the because it's got a negative in front of the t squared term, it's going to be an upside down parabola like this one. And what we want to do is work out, well, where's that maximum peak going to be, which we could differentiate to find, or if you remember your equations for the vertex of a parabola is given by minus b over 2a, where b is the thing in front of the unsquared term, the linear term. So this is equal to minus 2 over 2 times a, in this case, is minus 1. So this is equal to 1. So we've got at 1 second, it's reflected about this. So then if we substitute in our 1 second, we have x at 1 second is 5 plus 2 minus 1, and so this is equal to 6 meters. So it gets up to 6 meters at 1 second, and then it starts coming back down like this, and we need to evaluate it at the final position, which we've done here, and this was 15 minus 25, so that was minus 10 meters. So here we've got minus 10 meters, and this is 5 seconds. So in the first second, it travels from 5 meters to 6 meters, so that's 1 meter. And then it travels from 6 meters down to 0, and then down to minus 10 meters. So here it's going a further 6 meters, and then here it's going a further 10 meters. So the total distance that it's traveled is equal to total distance is equal to 17 meters. Okay, part 3 of this question then asks, what is the average velocity of the particle in the first 5 seconds? So average velocity is equal to delta x over delta t, and we calculated delta x in this first part. So that's minus 15 over delta t, it was 5 seconds. So this is minus 3 meters per second. And this is along the x-axis, so in the negative x direction, back that way. And then part 4 asks us, what is the instantaneous velocity of the particle at t equals 0 and t equals 5? Okay, so the instantaneous velocity v is equal to dx dt. So we're going to have to differentiate our expression for x here. So when we do that, when we differentiate 5, we get 0. When we differentiate 2t, we get 2. And then when we differentiate minus t squared, we get minus 2t. So v at 0 is equal to 2 minus 2 times 0, which is equal to 2 meters per second, and that's positive, so in the positive x direction. And v at 5 seconds is equal to 2 minus 2 times 5, which is equal to minus 8 meters per second. So it's now going in the negative x direction, so back. Okay, now as we go on in physics, SI units are going to be really important. So SI units are System International, so they're an internationally agreed system of units that everybody uses, so that everybody can understand everybody else's results. So there are 7 SI units, and every other unit can be made up from a combination of these units. So some of them you're probably familiar with, like kilogram is the SI unit for mass, meters for distance, s seconds for time, amperes for current, kelvins for temperature, you'll be learning about that in the thermal physics topic, moles tell you about the amount of matter contained within something, and then candelabras, which you won't see in this course, is related to the luminosity of something. So we'll sometimes need to convert from one set of units to another. So the common units that we'll be using at the start is, well, distance is measured in meters, and velocity, we saw that velocity was equal to dx dt, so that's meters divided by the units for time, so meters per second. And next lecture we'll be seeing acceleration, which is meters per second per second. But how do we nicely convert something like 60 kilometers per hour into meters per second? Okay, so if we want to convert something like 60 kilometers per hour into meters per second, we can write 60 kilometers per hour. And now we want to get it into meters. So if we multiply this by, we've got 1,000 meters in a kilometer, you can see we've got a kilometre in the numerator and 1 in the denominator. So those are actually going to cancel each other out, which will be nice. Now we will also want to get rid of this hours. And so if we say, well, there's 60 times 60 seconds in an hour, then we'll be cancelling out this hour in the numerator, with the 1 in the denominator. And our units which are left over is we'll have meters per second. So we can solve this on the calculator and we end up with 16.7 meters per second. Now, the other thing that you'll come across a lot in physics is prefixes. Sometimes we want to talk about really big numbers, and sometimes we want to talk about really small numbers. So with these really big ones, you've probably come across them in computing. So we've got tera, so that's 10 to the 12. Giga is 10 to the 9. Mega, 10 to the 6. Kilo is 10 to the 3, so kilometers, for example. Now, getting smaller, we've got centi, so centimeters, 10 to the minus 2. Milli, which is 10 to the minus 3. Micro is 10 to the minus 6. Nano is 10 to the minus 9, all the way down to pico, which is 10 to the minus 12. And it's not here, but there's femto, which is 10 to the minus 15. So sometimes we need to convert between these. So one example is we could be asked how many centimeters in a kilometer. Well, a kilometer is 1,000 meters and a centimeter is 0.01 meters. And so dividing 1,000 by 0.01 will give us the answer to this, which gives us 100,000 centimeters in a kilometer. Now, significant figures are something that you're going to need to use a lot as well. So how many significant figures does each of these numbers have? Well, 55, we've got 2 significant figures there. We've got the 5 and the 5 both being significant, so this is 2. Okay, 30. Now, this one can actually have 1 significant figure because this 0 may or may not be significant. So 30 is actually special. It can have 1 or it can have 2, because if it's just written as 30, we don't know if this 0 is significant or not. So this is 1 or 2 significant figures. 121, we've got 3 significant figures there, 1, 2, 3. 500, this is like the 30. We don't know if this 0 is significant. We don't know if this 0 is significant. So this one here is 1 or 2 or 3. And 22.3, we've got the 1 decimal place here, which is significant, and then 2 on this side. So this one here has 3 significant figures. Now, it's important whenever you're asked to give an answer, you should give your answer with the same number of significant figures as the piece of data used in the calculation with the least number of significant figures. So I have not been doing that in this lecture so far. So we'll start to worry about this now. So how many significant figures do you answer this question to? So a car travels northwards at 62 kilometers per hour. That's 2 significant figures. For 51 minutes. That's 2 sig fig as well. And then in an easterly direction at 55.5, that's 3 sig fig kilometers per hour for 15 minutes. That's 2 sig fig. What is its displacement in meters per second? Okay, so we first asked how many significant figures do you answer this question to? So the number of significant figures is 2, 2, 3, and 2. So we choose the smallest of those, which is 2. So we answer this to 2 sig fig. And then it tells us to now answer this question. Okay, so let's start by working out how far it's gone northwards. So the distance that it's traveled is going to be equal to the velocity times the time. So this is just rearranging our equation that the velocity is equal to the displacement over the time. And so this is going to be 62 kilometers per hour. So that's 62 kilometers per hour, and then we times it by 1,000 and divide it by 60 times 60 to get it into meters per second. So this is in meters per second, and the time it travels for is 51 meters. So we also need this in seconds. So we're putting everything into SI units so that we don't make a mistake. So 51 times 60, that's in seconds. So we can say, see meters per second times seconds. That's going to give us an answer in meters. And so this is going to be 52,700 meters north. And then delta x2, it then goes in an easterly direction, and so that is at 55.5 times 1,000 over 60 times 60 times the time, which is the 15 times 60. And solving that, we get 13,875 meters, and in this case this is going in an easterly direction, east. So that has not answered it to two significant figures yet. So it doesn't tell us if we have to answer it in unit vector notation or with a magnitude and direction. So if we wanted to do it in unit vector notation, we would write our answer as 53,000, sorry, the pen isn't working very well, plus 13,000, sorry, that'll be 14,000 because it's to two significant figures, J, and then we do need our units, so meters. So that's one way we can do it. The other way we can do it is to draw them head to tail, and so we've got going up, and this is the 52,700, and then we've got going east, which is the 13,875, and this is our resultant here. So to work out this, we just use Pythagoras. So that's the square root of 13,875 squared plus the 52,700 squared, which, sorry, you can barely read. And then solving this on the calculator, we get 54,000 meters. Now I've just given that to two significant figures. I haven't included the extra figures here. And then we need to work out this angle theta. And so to work out that angle theta, we can just use tan theta is equal to 13,875 divided by 52,700. So solving that, we get theta is 15 degrees. So we can say north 15 degrees east is the final answer to two significant figures. Now, each lecture we're going to end with a few problems, 2 or 3 problems. We won't necessarily have time to complete these in class, but I will give you the solutions to them. It's a good idea for you to have a go at them, and then if you get stuck, refer to the solutions. Okay, so I've pasted the question up here. It says a jogger runs at a constant speed of 10 kilometers per hour. So the speed is equal to 10 kilometers per hour. They run in a northerly direction for 25 minutes. So 25 minutes north. And then run in a westerly direction for 35 minutes. So then 35 minutes west. Now part 1 says give their displacement in meters in unit vector notation, with I being the easterly direction. Okay, so this is I, and J being the northerly direction. Okay, so we need to get the displacement in meters. So that's an SI unit. So let's convert this constant speed into a constant speed in meters per second. So we've got V is equal to 10 kilometers per hour. Now, if we convert it from kilometers to meters, there's 1,000 meters in 1 kilometer. And then we want to convert from hours to seconds. So there's 60 times 60 seconds in 1 hour. So that'll cancel out our hours and our kilometers, and we'll end up with meters per second. So effectively what we're doing is we're dividing 10 by 3.6. And when we do that, we end up with 2.78 meters per second. Okay, so let's see how far he goes north. He's running north like this, and it's 25 minutes at this speed. So we know that the distance is equal to the velocity times the time. So that's equal to 2.78. This is meters per second. So we actually need the time in seconds as well. It's 25 minutes, so that's times 25 times 60, because there's 60 seconds in a minute. And so this gives us the time in seconds. And so solving that, we end up with 4,166 meters. And this is in a northerly direction. So north is J. So we put a little unit vector after that. So we've got the initial distance, and now he runs for 35 minutes west. So west is in this direction. And so we use distance is equal to velocity times time again. The velocity is still 2.78. The time is now 35 minutes. So that's 35 times 60 to get it into seconds. And solving that, we end up with 5,838 meters. But what we're going to need is a displacement, which is a vector. So this is going in the negative I direction. So we'll put a negative there, and then we'll put an I after it. Okay, so he is basically going north like this, and then west like this, and ending up somewhere over here. But it's quite easy to give this displacement in unit vector notation, because we just add these together. As everything here is given to two significant figures, we should give our answer to two significant figures. So this is equal to, let's start with the I component, minus 5,800 I. And then we've got plus 4,200 J. And so that's our displacement in unit vector notation, and it's in meters. We need to include our unit. Okay, so that's part one. Now in part two, it asks us, what is the average velocity of the jogger? Okay, so the average velocity is equal to the change in the displacement over the change in the time. This is a vector. So this is that vector that we've just calculated here. So this is equal to minus 5,800 plus 4,200 J, this is I, over the time. And this is the total time here. So he's running for 25 minutes, then 35 minutes, and we want this to be in seconds. So we're going to times that by 60. So 25 plus 35, that's actually 60. So we've got 60 times 60 on the bottom. Solving this on the calculator, we end up with minus 1.6 I plus 1.2 J. And this is in meters per second. So that's how we solved that problem. So our next problem is a particle moves along the x-axis. Its position is described by the equation x is equal to 2t squared minus 7. And then we're going to need to look for its displacement, its distance, average velocity, and some instantaneous velocities. Now, a good way to start this question is with a diagram showing what this equation here means, because we'll need to know if our particle goes forwards, then backwards, or if it just keeps going in the one direction. So let's do a little graph, and we'll put time along the x-axis, and we'll put x along the y-axis. So at time 0, if we substitute 0 into here, you can see it starts at minus 7. So it starts at there. Now at 1 second, we've got 2 times 1 squared minus 7, so that's minus 5. So here it's like here. And then at 2 seconds, we've got 2 times 2 squared, so 2 times 4, so that's 8 minus 7, so it's up to 1 there. And then you can see it's getting bigger now as the square. So at 5 seconds, 2 times 5 squared, that's 2 times 25, so that's 50 minus 7. So what's that? 43. So we end up with a parabola type shape. So let's draw this shape here. It's a bit messy, but it's a parabola. And you can see it's got a minimum here. So if it was going backwards in time, it'd come back up here like this. Okay, so now we can use this to try and solve the problem. Part 1 says, what is the displacement of the particle in its first 5 seconds? Okay, so we want, it's only moving in the one dimension, in the x dimension. So the displacement is the final position minus the initial position. So we worked out that it ended up at 43 meters. So this is 43, and we said it started at 7 meters, so minus 7. And so this is 43 plus 7, so this gives us 50 meters. And this is along x. And it's a vector, so we need to give a direction. So we can say along the positive x axis. And then part 2 says, what distance does the particle travel in the first 5 seconds? So this one isn't too bad because it's not going backwards at all, it's only going forwards. If it only goes forwards, then the displacement and the distance are going to be the same. So the distance is equal to 50 meters. Part 3 then asks, what is the average velocity of the particle in the first 5 seconds? So we want average velocity, and so that'll be the displacement divided by the time. We've got our displacement is 50 meters along the x-axis, and the time is 5 seconds. So this is going to be equal to 10 meters per second along positive x-axis. So again, we've given the direction because of velocity is a vector. And then part 4 asks us, what is the instantaneous velocity? So to get instantaneous velocity, we need to use v is equal to dx dt. And so we'll be differentiating 2t squared minus 7 with respect to time, and differentiating this, we end up with 4t. So we want the instantaneous velocity at t equals 0. So when we substitute 0 in here, we get 0. Which is what we expect looking at our parabola. If we look at the tangent at t equals 0, which is the tangent down here, you can see it is a completely flat line. So the velocity should be 0. And then the velocity at 5 seconds, which is really related to the gradient of this slope at 5 seconds. We'll learn more about that in the next lecture. And so this is equal to 4 times 5, just substituting into this equation here. And so this is equal to 20 meters per second. And then again, we need to give a direction because it's still a vector. So along positive x axis. So that's how we solve that problem.